Chapter 17. Pointers. Who is looking at whom? In this chapter, I cover the two main kinds of variables, static and dynamic. These names refer to how memory is used for the storage of data. Dynamic variables are sometimes called pointer variables because they actually contain addresses that allow them to point to another location in the memory. A pointer variable has two uses. It allows the programmer to save memory by referral instead of copying everything, and it allows him to release the variable when he is finished with it. Finally, I will discuss how to declare and use pointer variables. In this chapter, static variables, dynamic variables, introduction of pointer variables, how pointer variables work, why use pointer variables, static versus dynamic variables. There are two kinds of variables, and before you understand the basic difference between them, you need to consider an analogy. Imagine you are taking an around-the-world trip where you will visit different countries in different climates. The first part of the trip you will expect to spend in northern countries where the climate is cold. The second part of the trip you will visit southern countries where the weather is warmer. Strategically, you will pack half your luggage with clothing for the cold weather and the rest of your luggage with clothing for the warmer climate in southern countries. After you spend the first part of the trip in the cold weather, you plan to send that luggage home so you don't have to continue to carry it around with you as literally excess baggage. Now you can travel more easily, carrying only what you need for the remainder of the trip. Variables can be likened to the baggage on a trip. Some variables you are stuck with for the entire program. You can't get rid of them, even if their purpose was long over and the first few minutes of running a long program. They are called static variables because they exist for the duration of a program. Other variables, called dynamic variables, are convenient in the way that they can be unloaded at any point through the execution of a program. Static and dynamic variables. Their role in memory. There are two classifications of variables beyond the types we mentioned earlier in the book. These classifications describe how variables use memory. The first classification of variables is called static. Static variables exist for the duration of a program. Once you declare a static variable, it occupies a spot in the memory of the computer until the program ends. All the variables we have studied so far have been static variables. Dynamic variables behave differently. They can be declared during the execution of a program. What that means is they can come into existence during the running of the program if they are needed. They can also be destroyed during the running of the program. When a dynamic variable is destroyed, the space it occupied in memory is released back to the computer. This is important if you are running a program that uses huge amounts of memory and you don't want to waste any of it on variables that no longer serve any purpose as the program continues to run. The pointer variable, a dynamic variable. In this section, we examine the pointer variable, which is a dynamic variable. A pointer variable, or pointer for short, is a variable that holds an address rather than a value. Think of a variable as a container. Normally, a variable holds a value. Regular variables look like holders with values inside. See Figure 17.1. Figure 17.1. 3 static variables are shown with their values inside. Answer 14.2. Result 65.62. Name Dorothy. Pointer variables, unlike static variables, do not contain values. They contain addresses that look like a combination of letters and numbers. See Figure 17.2. Figure 17.2. 3 pointer variables are shown with addresses inside of them. P, A114. S, CD2F. M, B009. Since pointer variables contain addresses where data is stored, programmers can make use of them in functions. Functions, as you may recall, often have parameters that are sent into the function to be manipulated. Some of these parameters are called variable or reference parameters. See Chapter 8. Reference parameters are really pointer variables because they allow you to refer to another location where contents are stored. Normally, when a variable is needed in a function, it needs to have all of its contents copied into a new memory spot for the function. A pointer variable just passes its address into the function so that the function can get at its contents without having to copy its contents. Programming with the pointer variables allows programmers to conserve memory. Imagine 4 separate functions that all alter the same variable, called check amount. If static variables are used, each function must have copies of that variable and will use memory to make those copies. If pointer variables are used instead, each function can simply store the address of check amount. This saves a lot of memory space. How a pointer variable works. Now that you know that pointers contain addresses, the question is, how do they work? The first step is to get the address that is contained in the pointer. The next step is to go to that address where another variable is found. Then you can go inside of the other variable to get its value. Because the pointer contains an address, it really points to another place in memory. At that other place in memory, you will find a variable that contains a value. See figure 17.3. Figure 17.3. A pointer is shown with its address. Another variable containing a value is shown at that address. P 4500, arrow pointing to 12, 450C location in memory. Operations associated with pointers. There are different tasks or operations associated with pointers regardless of the language you are using. Once you understand the concepts behind each of these tasks, you will be ready to learn the different syntax rules particular to each language. Let's examine each of these tasks. Declaring a point. When you declare a pointer, you are telling the compiler to treat the variable in a different way. The compiler will understand that it will be dealing with memory addresses rather than direct values. When you declare a pointer variable, you need to tell the compiler what type of value the pointer will ultimately be looking at. It is understood that a pointer will contain an address, but we need to tell the compiler an address for what type of variable. Will it contain an address to an integer, to a character, to a string, or to a record structure? These are important concerns for the compiler. Just like the declaration of a static variable, we first state the type of variable followed by the pointer's name. The only difference between static variable declaration and pointer variable declaration is the use of an intermediate symbol to indicate it is a pointer. In the C++ language, we use an asterisk between the pointer's name and the variable type it will point at. Int asterisk p. P will look at an integer. P will contain the address of an integer variable. P itself is not an integer. The pointer variable has a name, but the variable it looks at does not always have one. The other variable is known as the variable the pointer looks at. See figure 17.4. Figure 17.4. Two pointer variables are shown with their own variable names and the addresses they contain. At each address, another variable is shown containing a value and labeled what P looks at and what M looks at. P D116, what P looks at 14 D116. M AC1F, what M looks at -32 AC1F. P has an arrow, M does not, pointing to the right. Allocating memory for a pointer. The term allocate means to set aside for use. If you allocate funds for a project, such as building a bridge, you set aside funds to build the bridge. When you allocate memory, you are reserving memory for use by the pointer. The command to set aside the memory is the new command. This command is used with the type of variable the pointer will look at. the compiler will look for an available space, get the address of that space, and assign that address to the pointer. The pointer now contains that address. Consider the following example. Int star p. P is declared as a pointer variable. P equals new int. Memory is set aside, allocated for P. We don't have any control over the address that the compiler finds in memory for the pointer. The compiler will look for a place in memory that is open or unoccupied. It will then assign the address of that spot to the pointer. The next step is to assign a value to that address according to the type used in the declaration. Once you have allocated memory for a pointer, then you want to assign it. Assigning the variable at which the pointer looks. There are two kinds of assignments for pointer variables, depending on how you want the pointer to be used. The first type of assignment is when you assign the variable the pointer looks at it. The assignment is just like the other assignment statements we have used previously. The only difference is with this kind of assignment. The only difference with this kind of assignment is that we need to clearly tell the compiler that we wish to assign the variable the pointer looks at, not the pointer itself. Let's call the variable the pointer looks at the referred variable. Let's look at how we name this other variable. If we can use the correct syntax for naming the variable, then we use that name in the assignment statement to make the statement work. When calling this other variable, we use the asterisk symbol again, but we put it after the pointer name. Consider these three statements used with the pointer called p. Int asterisk p. The compiler is informed that p is a pointer. P equals new int. Memory is allocated for p. P asterisk equals 6. What p looks at is assigned the value. Here are some other examples of pointers being declared, then assigned after memory has been allocated to them. Char asterisk g. G is declared as a pointer to a character. G equals new character, new char. Memory is allocated to G. G asterisk equals M. What G looks at is given the value M. Double asterisk num. Num equals new double. Num asterisk equals 45.65. Caution. It is very important to use the asterisk symbol properly. In declaration statements, it is used on one side of the pointer name. In assignment statements, it is used on the other side of the pointer. Distinguishing between the pointer and the referred variable. In the following examples, consider each of the values in the variable. Either the value is an address contained in the pointer, or it is a value of the variable type referred to by the pointer. Also note the names of each variable. Both the pointer names and the variables referred to by the pointer names. See Figure 17.5. Figure 17.5. Each variable, whether a static variable or a dynamic pointer variable, is located at an address and contains something, either an address or a value. Pointer variables. First variable. Name of variable, P. Contents of variable, A113. Location of variable, C115. Name of next variable, P star, P asterisk. Contents of variable, 25. Location of variable, A113. In this section, we will examine statements that either use the pointer or use the referred variable. Because pointers contain addresses, sometimes it is necessary to consider the address container contained in a pointer. In the first example, we want to check to see whether two different pointers are looking at the same variable. The easiest way to do this is to compare the addresses contained in the pointers. Let's start by declaring two pointers and assigning their referred variables. Int asterisk p. Both p and m are declared as pointers. Int asterisk m. The compiler now knows they will contain addresses. P equals new int. M is equal to new int. Memory is set aside for both. P asterisk equals 15. The referred vars are assigned. M asterisk equals 34. Next, we want to compare the pointers themselves using a relational operator. Let's assume that P's address is AB14 and M's address is C12A. The next statement will compare their addresses to see if they are the same. Addresses contained in both P and M are compared. If P is equal to M. See out. These pointers are looking at the same variable. The compiler will check to see if the relational expression AB14 equals C12A is true, which it is not. If we use the following statement with this pointer variable, with the pointer variables, the relational expression will be true because AB14 does not equal C12A. If P does not equal M, see out, these pointers are not looking at the same variables. Let's look at some other examples where we use either the pointer or its referred variable. The statements are shown at left and the values printed on the screen are shown at right. Notice that for the last two examples, we do not know what the user will type, so the question mark indicates this fact. Examples. Cout P and L, AB14. Cout P star and L, 15. Cout M and L, C12A. Cout M star and L, 38. Letting the user assign P asterisk C in P asterisk question mark. Letting the user assign M asterisk C in M asterisk question mark. How to assign the pointer another pointer. So far we have assigned only the variables referred to by the pointers. It is also possible to assign the pointer instead itself. It is also possible to assign the pointer itself. You can assign the pointer an address contained in another pointer. This is equivalent to making two pointers look at the same variable. One pointer's address will be copied into another pointer variable after executing these statements. Int asterisk P, declaring a pointer to an int. Int asterisk snaker, declaring a pointer to an int. Snaker equals new int, allocating memory for the snaker. P equals snaker. P will look at the same variable as snaker. Note: as mentioned before, we have no control over the address the compiler assigns to a pointer when we set aside memory to the pointer. Deallocating memory. When we speak of deallocating memory, we really mean that we are releasing occupied space back to the compiler for its use. If you recall, it's like sending the luggage home during the long trip. How it works is best explained in this way. When we set aside memory for a pointer through the new command, the compiler finds a block of memory both suitable for the variable type and unoccupied and assigns that address to the pointer. The pointer is the gateway to that other variable's content. This variable, the one we call the variable looked at by the pointer, is the referred variable. If we need this variable for the duration of the program, it behaves much like the static variables and studied previously. However, if you find that you need more memory and this referred variable is no longer useful, then you can release this memory back to the compiler. Releasing the memory is called deallocating memory. When do we do this? Through the delete command. P is a pointer variable. Delete P. P's address is given back to the compiler. A variable containing some value occupies memory space. When the pointer used with the delete command, the address of the referred variable is returned to the compiler for future use. Note: deallocating memory is the same as releasing the memory occupied by the referral variable. This address is given back to the compiler for future use. Summary: this chapter introduced static variables and dynamic variables. Static variables exist for the duration of a program, while dynamic variables do not. The pointer variable is a dynamic variable which contains an address to a location in memory. At that other address is a variable called a referred variable, or the variable the pointer looks at. I gave different examples of the syntax for assigning the referred variable of a pointer. You have no control over the address the compiler chooses to set aside for a pointer. The pointer is given a spot in memory. This is called allocating memory for a pointer, and it is done through the new command. Likewise, releasing memory once referred to by a pointer is called deallocating memory, and this is executed with the delete command. The asterisk symbol is used in pointer syntax. When you declare a pointer variable, the asterisk is used in the declaration to indicate that a pointer is being declared rather than a static variable. All the variables we have worked with so far have been static variables.